Hello, everyone, and thank you for being with me today as we go through Aerospike client design and internals with a focus on timeout systems. My name is Dylan Welch. I'm an ecosystems engineer at Aerospike. I work on clients and database tools. Today's presentation will cover timeout systems in the Aerospike clients, including an overview of client and transaction connection logic. Aerospike is a complex distributed system of server nodes and clients. Its use of the network for coordinating cluster structure and serving requests means Aerospike needs to be able to handle lost node connections, timed out transactions, and surges in traffic. In addition, many use cases require special network behavior, such as TLS scenarios when connection creation is expensive or cloud deployments. Aerospike clients deal with these issues by using a dynamic and customizable connection system. Both client connection forming and timeout behavior can be modified via client and transaction policies that we will discuss during this talk. Before we get into timeout policy, let's look at how Aerospike clients initially connect to an Aerospike cluster. Most clients accept a list of hosts during client construction. These are seed nodes that the client tries to connect to in order to get information about the rest of the cluster. The client will try each of the seed nodes until it successfully connects to one. That's step one. That seed node will send information about the cluster, like addresses of other nodes, back to the client in step two. The client uses these other addresses to form cluster tend connections to each of the nodes in the cluster in step three. These connections are maintained in a client cluster tend thread that periodically checks the status of the nodes, client connections to them, and receives updated cluster information. Finally, a connection pool for each node is created in step four. These pools hold socket connections used for transaction processing with each node. Note that in some clients, like the Java and C client, pools are created per event loop per node if using Async. The Golang client is Async only and uses a pool of pools per node. Before we continue, we should keep in mind that Aerospike has many different clients. They don't all have the same client connection logic and policies. That said, most clients are based off the functionality and connection logic of the Java, C, and Go clients. So that's what we're focusing on in this presentation. From now on, please check slide headings for Java, C, and Golang to see which clients support which policies. Since the C# and Java client have similar timeout policies and behaviors, we'll focus on the Java client for the sake of brevity. There are more clients, but many of them embed the Java and C client for connection handling. These include the Python, Node.js, REST, and PHP clients, plus more. These clients usually have similar timeout and connection policies to the clients they embed. Some clients have sync and async modes that change connection pool behavior and allow for different timeout policies. In this presentation, I'm going to split covered policies into two groups. The first I call client timeout policies. These policies are used during client creation and are usually defined in some kind of client policy class. The policies we'll see are listed below. Login timeout is a client timeout policy that is used during optional user authentication the first time the client connects to the cluster. So it applies during connection to the seed nodes and establishing those cluster tend connections. MaxCons per node configures the maximum connections allowed for each node's corresponding connection pool in the client. If a transaction attempts to make a connection that would exceed MaxCons per nodes, it will fail with a max cons exceeded error, or something similar depending on the client. Now, there are sync and async versions of this policy in the Java and C clients, and they behave like this. In sync, max cons per node defines the maximum number of connections for each pool for each node. There's only connection pools, one for each node. In async, there is a connection pool per event loop per node. So here, the maximum number of connections for those pools in the event loops is async max cons per node divided by the number of event loops. And async max cons per node is set to max cons per node by default, and the default for max cons per node is 300 connections. So the async max cons per node and max cons per node policies should be coordinated with the server max connections config proto fd max. The number to keep in mind here is that the maximum possible connections to a node is the number of clients times 1 plus max cons per node. And that 1 comes from the cluster 10 connection. Connection queue size and limit connections to queue size function similarly to max cons per node, but for the Go client. Connection queue size is like max cons per node, but it does not enforce the connection creation limit. That is given to limit connections to queue size, which is true by default. Min-cons per node configures the minimum connections allowed for each node's corresponding connection pool. These connections are made when the client first establishes connections to the nodes. If the connection count falls below min-cons per node, the client will periodically open new connections to restore it. There are sync and async versions for min-cons per node, similar to async or to max-cons per node, and the formula is the same. Normally, transactions trigger the creation of connections when there's no available connections in the pools. This means that after client startup, when the connection pools are empty, or after a long period of inactivity when connections have been trimmed, the next burst of transactions will incur connection creation overhead. Min-cons per node can be used to mitigate this overhead by keeping some connections alive and in reserve. One thing to consider to avoid connection churn, consider setting the server config proto fd idle ms. That's how long a connection can be idle server side. In the client policy, max socket idle, which we'll discuss soon, to 0. This helps to avoid closing usable connections by relying on TCP keep alive to detect dead sockets. Warmup is similar to min-cons per node, but for the Go client. It's a method instead of a policy, and it's used to fill connection pools to a desired count. So anything greater than the pool size or 0 or less will just fill the connection pools. Otherwise, they're filled to count. And it's useful for the same things that min-cons per node is. The client policy timeout is used for initial connection time, not authentication. That's handled by login timeout. It applies to initial connections to seed nodes, to cluster 10 info calls. That's calls that the cluster 10 thread makes periodically to get updated information from the nodes, and to creating those initial minimum connections that min-cons per node configures. Max error rate sets the maximum allowed errors per node per error rate window. If the limit is exceeded, database commands to that node will throw a back-off exception. Counted errors are anything that causes a connection to close. This includes socket errors, timeouts, and the device overload return code. If max error rate is 0, then there's no limit, and it's 0 by default. Max error rate is useful as a circuit breaker or a back-off mechanism that can avoid overwhelming clusters. Error rate window defines the time window for max error rate. Max error rate is reset at the beginning of each error rate window and counted towards for error rate window time. Error rate window is measured in cluster tend iterations, and those are the value of the tend interval client policy, which is 1,000 milliseconds by default, plus the time it takes for the cluster tend thread to tend all nodes. So error rate window is one cluster tend interval by default. And again, with max error rate, this makes for a useful circuit breaker or back-off mechanism. Next, we'll go through transaction connection creation. So we'll use this diagram to go through the async transaction process. When a user's application makes a call that starts a transaction, that transaction is handled by a transaction thread, an event loop in the case of the Java client. All transactions start by identifying the node that has the data they are looking for. Some transactions, like scans, will need to contact multiple nodes. Next, the transaction thread tries to get connections from those nodes' corresponding pools, connection pools. If getting a transaction, or if the transaction thread fails to get a connection from the pool, it will create one. Unless, in the case of the Go client, where the transaction thread signals for another thread to create the connection, and then it starts its retry process. When the transaction thread has its connections, it will run the transaction on them. If the transaction times out, it is retried, or the connection is closed and discarded, depending on the timeout and policies in place. If it's successful, then the connection is returned to the connection pool. So the second group of policies are transaction policies. These are usually defined in read or write policies and passed to methods that initiate transactions, like get, put, or operate. And these apply to individual transactions. So max socket idle is a bit of an exception to the other transaction timeouts, since it is used with the client constructor and is client-wide. But max socket idle applies to transaction connections, so we're covering it here. Max socket idle represents the idle lifetime of a connection in the connection pool. Every time a connection is used, the transaction thread checks to see if it has exceeded max socket idle. If so, the connection is closed and discarded, and the transaction thread looks for another connection to use. Otherwise, the connection's deadline is extended by max socket idle and it's used. If a connection sits idle for max socket idle time in the connection pool, it will be closed and discarded from the pool, either by that transaction check or from periodic checks by the cluster tend thread. If max socket idle is 0, then it won't be checked by transactions, but connections will still be trimmed on a 55-second hard-coded limit by the cluster tend thread, unless they're protected by min-cons per node. So max socket idle can be set in accordance with your application's behavior to help mitigate connection churn. That's the excessive closing and opening of connections, and to reduce connection creation overhead. Total timeout acts as a deadline for active transactions. No retries are performed when total timeout is reached. Instead, the transaction is aborted and the connection is closed. Total timeout is tracked on the client, but also sent to the server depending on its value. So the client will probably time out first, but the server can too. If total timeout is 0, there will be no total timeout on active transactions, and transactions will remain active through their retry count. If a connection sits idle for socket timeout time during a transaction, the transaction will be retried if max retries, policy we'll cover soon, and total timeout have not been exceeded. If socket timeout is greater than total timeout and total timeout is greater than 0, then socket timeout will be set to total timeout. So basically you want socket timeout smaller than total timeout if you want it to take effect, if total timeout isn't 0. A socket timeout of 0 means only total timeout will be enforced, which does not trigger retries. However, a server timeout received before total timeout expires might still trigger a retry. Depending on the values of socket timeout and total timeout, the server is sent one of the two, or 0. Note that 0 prompts the server to use its default timeout of 1 second. The next slide covers these rules. So here's an overview of the rules in the Java client that determine which timeout is sent to the server. Because these may differ per client, and for the sake of brevity, I'm going to gloss over these here and let those who are interested return to these slides later. Max retries defines the number of retries allowed before an active transaction is aborted. Retries do not count the first attempt, so a transaction can be attempted max retries plus 1 times. Operations that aren't idempotent should not be retried, as they have potential to act on data multiple times. For this reason, the default retries for writes is 0, and the default for reads is 2. Timeout delay is a Java-only policy that offers a second chance to recycle transaction connections before they're closed after a socket read timeout. When timeout delay is non-zero and a transaction timeout occurs, an exception will be passed back to the user as normal. In the background, though, the socket will be drained for timeout delay time. If the transaction finishes during this time, the results are thrown out, but the connection is saved and put back in the pool. If the transaction does not finish in this time, the connection is closed and removed from the pool as normal. Connect timeout is only used for initial transaction connection creation and optional authentication, but it's currently only supported in the Java client, but coming to the C and C# clients soon. And this is useful in the case of TLS, for example, where connection creation is expensive. And this occurs when transaction tries to get a connection from the connection pool, but it can't, so it goes to create one. Connect timeout applies during that initial creation. So the Go client doesn't have a connect timeout policy, but it does offer similar functionality through the client policy timeout. Remember that the Go client transaction threads don't create their own connections. They signal another thread to do so. This thread creates connections using the client policy timeout. So if you want similar functionality to connect timeout in the Go client, you can use timeout. Sleep between retries provides a back-off mechanism by specifying a sleep period between retry attempts. The Java and C event loops are non-blocking, so they ignore this in async mode. The sleep is only triggered by errors that suggest a node is down or the cluster is reforming. So transaction socket timeouts won't trigger the sleep. The logic there being a quick retry will find a healthy node. It will be redirected to a healthy node anyways, and we'll cover that redirect process later. The default for read transactions is 0 because reads aren't locked out during cluster reform, and the default for write transactions is 0 because they aren't normally retried. Sleep multiplier is a Go client only config that allows for exponential backoff when used with sleep between retries. The time to wait between retries is governed by an interval variable, which is set to sleep between retries at the start of a transaction. If this is the first attempt of the transaction, just interval is used. On subsequent attempts, interval times sleep multiplier is used. An interval is static between attempts of the same transaction, so the interval between attempts will build. Now that we've covered types of timeout policy, let's look at working with timeouts as they happen. Note, the following slides and examples will focus on the Java client for the sake of brevity, but similar functionality is available in the other clients. So this example runs a write transaction and checks for timeouts during it. And note that this example focuses on timeouts that occur during a transaction, but other transaction-related errors and timeouts could occur. For example, the back-off error, which is triggered by max error rate, and the error connection, which is for a failed connection. So you can see here, create a bin, we do the write, checking for the exception timeout. So what does this timeout actually look like when we encounter it? Well, in the Java client, it comes in the form of the Aerospike exception.timeout. Other clients have similar constructs with similar info, but let's take a look at what each field means here. So the client timeout string tells us that the client initiated this timeout, not the server. Iteration tells us which attempt we were on when this transaction failed. The connect field says what the connect timeout policy for the transaction was. Socket timeout says the socket timeout. The total timeout policy, max retries policy. And the node gives the unique node ID or name and its IP and port. Then the in doubt field tells us whether the client thinks the transaction could have completed anyways server side. So say, for instance, you send a write transaction to the server, times out on the client, but maybe the server finishes processing it. In doubt will be marked true if the client thinks that could be the case. So Aerospike's ability to replicate data for reliability creates the need to specify how that data should be accessed, and which copies should be read or written, and in what order. In the event of a retry, the transaction can try contacting different nodes that replicate the desired data based on the replica policy. The Java client's default replica policy is called sequence. Under sequence, the master node for the desired data is contacted first, but if a connection failure or socket timeout occurs, one of the nodes containing the replica data is tried next. Multiple different sequence policies exist, or replica policies exist other than sequence. So let's bring this all together by having a look at an example. We can see that we start with the specifying of our seed nodes. Here it's just one host, the local host, and a creation of a client policy to customize our timeouts. We set the policy login timeout to 2000 milliseconds, timeout to 1000 milliseconds, max socket idle to 30 seconds, so connections will be trimmed a little bit more quickly here. We are using auth, so we set the user and password, and then create the client using our client policy. Next, we write a record just to read later, so we use the default write policy. And then we do a read with a custom policy. So we set the total timeout to 1000 milliseconds, that's the deadline for the transaction. Set socket timeout to 250 milliseconds, so theoretically we have time for 4 attempts here. And then set max retries to 3. 3 plus the first initial attempt gives us 4 attempts to use up that 250 millisecond socket timeout. And then we actually do the read using the policy. Here's an example in the Go client, in case people want to go back and have a look at this later in a different language. It's the same example though. So some common pitfalls concerning timeouts that we run into. You want to be careful on batch retries. Batch retries redirect each key requested to their replica node, so this can result in a ton of batch subcommands. So try to keep those to a minimum. Consider the trade-offs when you're setting your timeouts. So depending on your application's behavior, some things to consider. Shorter timeouts mean faster retries and potentially less of an impact if a node is failing, since they'll find a healthy node faster. But shorter timeouts also mean more timeouts when nodes are slow, potentially leading to connection churn and hitting the cluster harder. Another thing to keep in mind is to make sure that the server's proto-FD max config, which is responsible for the maximum amount of connections, is coordinated with the client's max cons per node policy. Then you can use that formula where the maximum possible connections to a node is the number of clients times 1 plus max cons per node, and that 1 is from the cluster tend connection. So key takeaways here, timeouts change the behavior of a client and its transaction connections. They are usually exposed in policy classes, client or transaction. Connect timeout can be used to accommodate expensive connections like during TLS. Total timeout is a sort of absolute deadline for connection or for transactions. And max retries defines how many times transactions can be retried. Socket timeout kind of plays hand in hand with that, defining how long an active transaction socket can sit idle, but also triggering many of those retries. So use these tools to try and avoid expensive connection churn. That's the unnecessary maintaining and creating of connections or closing them and reopening them. Try to find a balance with your application. Thank you very much. I've included some more information here for any of you who are curious, and please feel free to stick around for the Q&A section.
That's a great talk, Dylan. It's very useful, and it answered many questions you and I had. So thanks for that. So there are a couple of questions already in the, people have asked them in the channel, Q&A channel here. And so I think there is, I think you did provide some links which I have already posted on the channel, but let's start with the question from Dennis. Please see whether you can, elaborate on it or you have anything to add to that. Do you have any best practices for async client loop threads number, connections for loop thread? That's first part. And the second part, the same question is also, do you have any metrics available inside the client which are available from outside, like new connections open rate? Do you have anything more to add to that? You pointed a couple of links there.
Sure, yeah. So like you said, I left a few links there for some more information. But yeah, one for the first part about best practices for the event loop connections. You definitely want to make sure that that async max cons per node config is set correctly and coordinated with whatever your max connection count per node is on the server, that proto-FD max. So that formula there for each of those connection pools per event loop, the max connections that they get was that async max cons per node divided by the number of event loops. So just keep in mind that that's the amount of connections that those event loop pools will be able to use, and set them accordingly to how many, what the maximum amount of connections you expect to a node in the cluster to be. Could you repeat that last part, Neil? Sorry, it slipped my memory.
Sure, it is. The second part was, are there any metrics available inside the client which are available from outside? So do they have access to some of these metrics through the logs or any other way?
Sure, yeah.
Yeah, the example is new connections open rate.
New connections open rate. Yeah. Specifically, new connections open rate, I'm not sure, but there are similar stats available. And you can get them through logging in the client, or you can get them through many of the clients will have stats APIs that are available. Like one of those links that I sent there is to a statistics class for the Java client, which exposes connection related statistics. So you can check those out, and other clients have similar methods.
Great. So always wondering, there are also, some of these timeouts and retry configuration parameters on the server side. How do they interact with the client side parameters? So the question I posted on the channel is, how should client timeout policies be coordinated with the server configuration? Are there any, quick thoughts on that?
Yeah, sure. So, I mean, depending on the application and the use case, there's like lots of configuration, lots of thought that can go into it. But there's a few things off the top of my head and a few things that have to do specifically with timeouts and client timeout policy. So as far as those go, one is the Proto FD Max, which I mentioned already, which is the server config for the maximum number of connections per node. You want to make sure that you coordinate that with your client's max cons per node and min cons per node to make sure that the client isn't trying to use too many connections or using too little. So that's one of them. Another would be Proto FD idle MS, which I think I mentioned briefly. That is the server config for how long a client connection can sit idle to the server. So you want to figure that in conjunction with the client's max socket idle config to make sure that they are cooperating there.
Yeah, that's great. So another, interesting topic is, in the discussion of connections and timeouts is the churn. Kind of connections are being created and then removed, and there's a constant churn that happens. So can you sort of shed light on what are the causes of it and how to address those?
Yeah, sure. So connection churn is definitely an important topic and has to do with these client timeout policies and connection policies in particular. So connection churn is just when you are opening and closing, opening or closing too many connections. Maybe you're doing it excessively, and if the client was configured correctly, then you wouldn't have to open or close so many connections. And establishing those connections can be really expensive, especially if you're using TLS or something like that. So in order to help avoid that, you want to use things like min cons per node. Say, for instance, if your application that's using Aerospike is one that expects spikes in traffic, in between those spikes in traffic, the client is probably going to trim inactive connections from the connection pools. So during each spike, there might be overhead where transactions have to create a lot of connections in order to keep up. But if you use min cons per node to keep some connections in reserve for the next spike, so they're not closed during the downtime, then that overhead will be lessened when a critical spike in traffic happens.
Right. Apart from the spike in traffic, are there any other causes of the churn that come to mind, such as the node being slow potentially, or some activity happening on the node that is not related to traffic necessarily?
Yeah, there could be. I think there definitely could be other causes. I mean, one that comes to mind is not so much node related, but it's just the client related during client startup. So if you're bringing client instances up, they are going to have to create connections when they start processing transactions. So you can use min cons per node to lessen the overhead by creating those connections up front before you start processing your transactions. Others might be, if you're interacting with nodes that are having issues maybe in the cluster, and your retries aren't configured to find the best node more quickly, or maybe the replica policy isn't configured correctly, then you might end up closing connections or hitting a node that is, that could be avoided basically via other configuration.
Okay, no, that's great. I think so. There's a lot of useful information shared, and thanks, Dylan, for that. And I think we are getting pings that the session is, the time is over. So thanks again for attending this session. Thanks, Dylan, for a great informative session. And, there's a lot of useful information there. And thanks for answering those questions.
Great. Thank you very much, everyone.